done a wide variety of work in numerous areas such as non-convex optimization, neural networks for small embedded systems, and generally provable bounds for machine learning. So with that.
Thanks, Harish. First of all, thanks to the organizers for this wonderful event, and also thanks for giving me a chance to speak here. This talk is based on a bunch of projects that I've done with some amazing set of collaborators, including Praneeth, who for some curious reason just left before the talk. This talk is about learning with outliers. That is, suppose our training data has a bunch of outliers. How do we still learn a machine learning model that is good, that has good generalization performance? And for this problem, we'll be following a very simple and general technique that is based on thresholding. And I'll try to convince you that this technique, although looks very simple and somewhat ad hoc, but still it leads to some very interesting results for a variety of problems, including robust regression, robust PCA, etc. In this talk, I'll mostly focus on the problem of robust regression, but I'll try to give a little bit of flavor of our work on robust PCA. So when we are training machine learning models, we have to deal with the data. And the data never comes in a very pristine form. Like there will be some outliers always in the data. These outliers might be there because of a bunch of reasons. They might be due to some data collection error, maybe say some simple bug in your script. It might be there because of some issues in the measurement system. It might be there because of some adversarial corruption, because somebody was trying to game your machine learning system. But whatever the reason, you can have this bunch of outliers. And the goal of this line of work is to learn a model that will be robust to these outliers. Now we are overloading this term robustness, and in last talk also there was a discussion about robust optimization, and in general there has been a lot of work on robust optimization or robust learning. So here let me just differentiate this line of work with some of those robust adversarial example work. Here we have in training data which can have outliers, and we still want to learn a model. Our test data is nice, like test data is whatever pristine. Whereas in that line of work, training data is nice, but the test data might have some adversarial examples, or test data might be generated by some adversary, and you still want to be robust to those. So they are totally orthogonal to each other. Now, for this line of work, let me give a couple of motivating applications. So first come from the domain of robust recommendation system. Suppose you have a bunch of users, bunch of movies, and some of the users have rated some of the movies. Now, a recommendation system will try to fill this matrix so that it can recommend movies to the users. In general, most of the ratings would be given by the users in some sort of nice, reasonable manner. But you can have some studios hiring some users who will go and rate their movies very highly and rate other studios' movies very poorly. That is, you might have a small number of aberrations or outliers, and the goal will be to still learn a recommendation system, a matrix that will be robust to these outliers. Similarly, you might want to build a classifier that will detect malicious URLs. Now, even the training data itself for this figuring out if a URL is malicious or not might have some outliers. And how do you deal with those set of outliers? Another very different type of applications come from the domain of video analysis, where suppose you are given a video captured from a fixed camera, and you want to do a background foreground separation. That is, you want a background like this, and you want to capture the foreground, and you want to do some analysis on top of it. So why is this robust learning problem? Well, you can think that your background is almost constant. It's a low rank matrix. And then this foreground is the outlier. It is a very sparse outlier. And your goal is to somehow ignore this sparse outlier and just learn this low rank background matrix. Fake news. Well, I mean, I guess that can be done, but I'm not a video analysis expert, so I wouldn't be able to comment. And also, I think nowadays people have much more advanced technology to do that. So I'm not sure this work will be very useful there. All right. So let's set up some notation for this learning with outliers. Using this. Okay. So suppose you are given a bunch of data points. Some of them are outliers. Let's call this set S star. and the remaining set of points are inliers. And these data points are, at least the inliers, let's say, are coming from some nice distribution. Say you can write down the empirical risk minimization or maximum likelihood estimation problem for them. And your correct model that we call W star is essentially obtained by solving your empirical risk minimization problem only over the inliers. But you don't know where those inliers are. And that's the challenge. That is, you want to find your correct model despite presence of these outliers. Right? So this robust learning problem has been around forever. And in 1980s, there was a lot of work on this in the statistics community. Huber and Rosesso and there was a bunch of very, very well-known statisticians who gave very interesting estimators for this problem. And in many cases, their estimators had optimal rate, at least for small dimension. So it seemed like that the problem is solved. But in last 2-3 years or maybe 5 years, there's been a lot of excitement in the area. So what's the reason? What happened? So it turned out that the statisticians didn't really care for high dimensional data, which is bread and butter of modern machine learning. And they also didn't care much for computation. Many of their estimators were actually exponential time. So that then, sort of opened our eyes to some very basic problems. For example, in 2016, there were a couple of very interesting papers on robust mean estimation. So the problem is as easy as it comes. I give you a bunch of data points coming from a distribution. I add a few outliers. And now your goal is to robustly estimate the mean, the true mean of the distribution. And that problem itself was open till 2016, like at least using an efficient method till 2016. And when Vempala and Rao, as well as Diclo Nichols and his co-authors, came up with very interesting solutions to solve the problem. Now, in this line of work, the technology or the philosophy that we are following is based on a very simple thresholding idea. So the observation is that if you knew the outliers and your inliers, and you compute your W star based on those inliers, then the resulting objective function values is small for each of those inliers. It's fairly small. So this is one simple observation. So now the approach is extremely simple. Let's say I knew my true model, then I can estimate these outliers fairly easily because I will just compute my loss function or objective function value for each of the point, and the points that have highest loss, they will most likely be my outliers. On the other hand, if I knew my inliers, then I can just solve my usual optimization problem and obtain the model. But the issue is that I don't know the true model, I don't know the set of outliers. In fact, that's the main issue. So what we can do is, so we have a chicken and egg problem, but there is a very simple sort of, solution to it, which is that be optimistic. That is, what we will do is, we will start with a very simple initialization. Let's say initially we'll say that we don't have any outliers at all. We will train a model based on our current estimate of inliers. That gives us a current estimate of the true model. Then we will find out all the points that have very large loss. And we will say that, oh, those guys are outliers, and we'll threshold them away and just iterate. So this is as easy as it can come. But it turns out that this very simple algorithm, with a little bit more bells and whistles, can solve several interesting problems. Now, if you look at the analysis of this algorithm, yeah. K as in the number of outliers? That's a great question. In general, either you have an estimate of what's the fraction of outliers in your data, or you might have to assume that I have a very clean test data, and then I will do a cross validation on that. That is, on that clean test data, I will figure out what is my accuracy. Whatever gives me highest accuracy, I'll select that number of outliers.
So for a small number, no K, with no number of that, by all.
Yeah, but typically, yeah, I agree. But typically, when we are talking about this fraction of outliers, it's going to be a constant fraction of the data points. So if I have 1,000,000 data points, I am working on algorithms that should at least allow, say, 100,000 outliers, in which case those approaches will not work. 100,000, let's say around 10%, around 10%. Well, clustering need not give you, so we'll talk about the problems. In many problems, clustering will not be able to solve this. Yeah. Yes. So I'm not claiming that this algorithm will work for every function for every setting. We will show that it works for a couple of problems in couple of like in very specific settings. Otherwise, this problem algorithm is just sort of very ad hoc, has no theoretical foundation. All right. So, but let's look at some good properties of this algorithm. So, if you look at the total running time of this algorithm, it's the number of iteration multiplied by the time required to solve your standard optimization problem. In general, we have very good solutions for solving the standard optimization problem. For each of these small problems like regression or principal components, we have developed very interesting algorithms over the ages. We want to leverage those algorithms. So this algorithm is using only those standard procedures in each iteration. But the main issue is that the number of iterations might be very large. It might not even converge ever. It might, like the number of iterations that you might need to run might be infinite. And even after that, the resulting solution might not be good. But if your problem or the function f has particular nice structure, and if your data is nice, then we can show that for a variety of problems, such a very simple approach with some bells and whistles will converge to the global optima. So to convince you that that holds true, let's look at a couple of these problems. So the first problem comes from the domain of regression, like it's as easy problem as it comes. Suppose, so let's first look at the standard regression setting. Suppose you have this bunch of data points xi's coming from some nice distribution. Let's say all of them are coming from a Gaussian distribution. And you have a parameter vector w star. For this xi's, the observation yi is given by just a simple inner product between w star and xi with some small amount of noise. Okay. Now, if you run standard least squares regression here, you know that you'll be able to estimate w star up to this much error. And this error is information theoretically optimal. That is, you cannot hope to do any better than this. So that's great. We understand our standard regression problem. Now let's change this problem a little bit. Suppose an adversary comes and looks at a few of these data points and then corrupts the target for them arbitrarily. So yi's are corrupted arbitrarily, right? And now the question is, can we solve this problem? Then can we still recover this w star as well as what we could do earlier? Now, if you apply a standard least squares regression, this is not going to work. Unfortunately, clustering is also not going to work because your data points xi's are still the same. It's just the yi's that are corrupted. And if you try to cluster your yi's, you might not have any information. So simple clustering ideas are also not going to work. Okay. So how do you solve this problem? And as I mentioned, if you apply standard linear regression, this is the resulting solution can be really, really bad with very, very small number of outliers. Yeah, so I have a small fraction of data points that adversary can look and corrupt arbitrarily. We will consider one more adversarial model later. Yeah, although adversary should not add very large values there because then it will become very obvious. So the adversary will corrupt somewhere close to the normal values for yi's. That's precisely the algorithm, right? And the main goal is to show why that really works. So as Sandeep was alluding, the algorithm is extremely simple. To motivate this algorithm, we are just sort of making these couple of observations. If I knew true w star, then I can find all the points that lie really far from this line, throw them away. If I knew this clean set of points and these outliers, then I can also recover my w star using standard least squares regression after throwing those outliers. But we don't know w star and this clean set of points, so we will apply a very simple iterative algorithm. That is, we will have an estimate of the true model. Let's say initially we have an estimate of the outliers, and we will remove those outliers, run least squares regression, find out the residual for each of the point. All the points that have high residual, we will throw them away, and then we will re-estimate our model, and we will just iterate like this. So extremely simple algorithm. Again, each iteration of this algorithm is solving just a least squares regression problem. We know how to solve that problem fairly well, and we are doing simple thresholding. So algorithm can be implemented very easily, right? But The interesting thing is that this very simple algorithm under some fairly simple constraints leads to the optimal solution. So what's the result here? So let's say we don't have any noise in the system. That is y is equal to given by the true model value, that is x times w star, but with some adversarial corruptions b. This vector b, which is added by the adversary, is sparse because adversary can corrupt only an alpha fraction of points. And suppose alpha is fairly small. Let's say it's 1 by 100. So we are corrupting say 1% of the data points. And each of our data point itself is coming from a nice distribution. Let's say it's a sub-Gaussian distribution with some covariance matrix. And we have enough data point that let's say we have d log d data points where d is the dimensionality. Then what we show is that after just around log 1 or epsilon iterations, you will be able to estimate your true solution up to epsilon error. So you have a linear rate of convergence to your optimal solution. And note that we are going to estimate our W star exactly. So although let's say 1% of the data points are corrupted arbitrarily, still you are estimating W star exactly. There is no loss in accuracy in W star. So it's as if the outliers were not even there, right? And the total running time of the algorithm is around order nd log 1 epsilon, which is nearly optimal to this log 1 epsilon factor. All right, so let's consider a slightly more interesting case when on top of this thing, we also have a small amount of sub-Gaussian noise. That is, in each of our observation, we have a small amount of white noise, okay? So even in this setting, like under exactly the same set of constraints, we'll be able to estimate W star up to this small error in a small number of iteration. So this small error sort of says that we'll be able to estimate W star up to standard deviation of the noise. So here again, I mean the number of iterations is good, but the estimation error is not optimal. Earlier, if you remember, the estimation error was going down with the number of points that you have. So if you had infinite many points, the estimation error was 0. Here we won't be able to say that. The estimation error will be sigma no matter what. Okay. So we'll revisit this question later. If we can estimate W star optimally, that is asymptotically with infinite many points, can we estimate W star exactly despite presence of outliers? Yeah, all those things are sitting here. I'm ignoring all of them. Mm-hmm. Sure. No, so here, no, this result will not say that. Right? This result is catering to situations when B is the worst case. When adversary comes and tries to move you as far as possible from W star, is like adversary is not helping you. And sorry, I spoke bit early. I didn't listen to Devrat's question properly. Let me confess. So these results are all with high probability because like ultimately the condition that we get out of these things is deterministic condition that holds with high probability, and then everything holds.
So if you think that significant this means that your outliers are not from and perhaps that your example when something you present it work or
yes, the algorithm will work, or at least a variant of algorithm will work, and in that situation we'll have much better result. So that's what I will come to in next 3 slides. Okay. Yeah. Log 1 or epsilon, I'm not sure. Maybe, yeah, I'm not sure. There is no low bounds here. And in fact, similarly for the sigma, in this setting also, we don't know of any lower bound. Okay, all right. Okay, so let's just look at a couple of examples of how this works in practice. So we use this algorithm to do a little bit of, denoising of faces. So suppose, this was this face, but it was corrupted in a very peculiar manner. So it's not random noise. And if you apply a standard, so here what you will do is you will try to denoise this face by fitting it in a dictionary. That is, you have a dictionary of faces, and you will say that I will try to represent this face or this image in the dictionary of faces, and hopefully it will denoise it. And here you see that if you apply standard linear regression, the resulting solution is very bad. So linear regression is very like it's affected quite a bit with these outliers. But if you run our algorithm, because it's an iterative algorithm, slowly it will clean up the whole thing, and in the final iterations, you get pretty much the same thing. Yeah, noise is these two black things. All right, any more questions? And so, sorry, I didn't explain it properly maybe. So what you are given is this image with these two corruptions. These two strips are corruptions, right? So now you will say that this is my y vector, okay? This is my observations. I will try to fit this observation in a dictionary of faces. That is, I have bunch of these faces or dictionary items. I will try to find some coefficients of this dictionary items so that it gives you back this image, right? And in general, it's well known that this sort of fitting is very good for denoising. But here the noise, which is these two strips, are very peculiar. They are not random noise, because of which if you apply standard regression, the answer, like the resulting solution is poor. But if you apply our method, the final solution is very good. So it is able to figure out that these are outliers and throw them away. All right. So for this problem, there is another way of formulating it as an L1, like L0 learning problem, or learning with L0 constraint, and you can relax it using what's called L1 optimization or L1 regularization. So it's very similar to a very popular lasso problem. There are some interesting theoretical results for this problem, but when you apply it in practice, then we observe that these L1 based methods are much slower to converge compared to our method. Now you can also apply this type of technique in deep learning. So let's say if you want to do a time series classification, many times what happens is that these time series themselves are labeled incorrectly, because you might have a very big window and you will label every single sub window of this big window as containing a certain event. Let's say that event is whether a person spoke a certain keyword. But you know that only one window or a few windows in this really captures the true event. Everything else is outlier or garbage. But people still run standard deep learning methods on it to figure out if a particular window has a particular event or not, say a particular keyword. And what we observe is that on top of that, if you can apply our thresholding based technique, then we can improve even those standard deep learning solutions. So for example, here if you want to do some sort of activity recognition in this time series data, your baseline algorithm will give 90% accuracy. And by just using this thresholding based approach, we can improve it to 92%. And this is deep learning, so 2% is a big deal there in general. And similarly for detecting keywords in audio or for detecting gestures in your time series data, you observe that by using this robust technique, you can improve the accuracy. One interesting observation here is that as you are increasing the size of the network, the advantage that is given by this thresholding technique or this robust technique decreases, which sort of indicates that as the network size is increasing, the neural network itself has become capable of absorbing these outliers and ignoring them. So it's a very sort of interesting line of research to show that you can solve these robust optimization problems using these neural networks with over-parameterized neural networks. That is where you are putting nodes more than what you really need. But that's for another talk. Yeah. The title was misleading. Sorry, I didn't get your question. Mm. No, actually, so is there a question or should I move to the next slide? Okay, all right. So, so now I'll come to the question that you asked earlier, which is that of oblivious adversary. That suppose adversary is not looking at all your data points and corrupting in a very malicious manner. Let's say adversary is corrupting some things, but the adversary cannot look at your data points. then what happens? So we call this as an oblivious adversary. And the question is, in that situation, can you do better? And it turns out that yes, that's why I'm presenting it. But for that, we will be using slightly different algorithm or slightly different formulation of the problem. So let me recall the problem. You are given this vector y as inner product of x and w star with some adversarial corruption and some white noise. Right? Each of these data points are coming from some fixed distribution, and this adversarial corruption is say alpha n sparse, right? So you can write this problem as a L0 minimization problem or a least squares problem under L0 constraint. That is, you want to find W and B which fits your observation as well as possible, but this B vector is sparse. It has say alpha n non-zeros only, right? This can be equivalently written as this formulation because your W doesn't have any constraint. So for a given B, you can optimize the W using least squares. And what you observe is finally that you want to minimize this residual and your B vector should be sparse, right? Now for this problem, you can apply a very simple projected gradient descent method. That is, you have some iterate BT, you do you do a gradient descent. Now resulting BT plus 1 will not be sparse. So what you do is you project onto the set of sparse vectors. Projection onto the set of sparse vectors again is easy, although it's a non-convex set, but the projection is easy. All you have to do is sort all your sort this vector BT plus 1, take the largest S elements, let's say S is alpha n, take largest alpha n elements and threshold everything else to 0. So that will be a alpha n sparse vector and it will be the optimal vector here. Okay. So again, very simple algorithm. It's very easy to implement it because each of this step is order ND and the projection is also just order N. So fairly simple algorithm, but again, how many iterations of this algorithm will we need to take? It turns out that under similar assumptions, we will need just log 1 or epsilon iterations. So after log 1 or epsilon iterations, we will be able to recover this optimal parameter W star up to this information theoretically optimal rate. So this says that now if you take your n to be infinity, we will be able to estimate W star exactly despite presence of this white noise. Okay. And so this is sort of very satisfying in the sense that it says that even if your problem has outliers, it doesn't matter. We will be still be able to do as well as what you could have done in outlier free setting. Okay. All right. So now